So, in the last video, we looked at how all of the orbitals where L equals 0 all have the same shape. They're all what we call s orbitals, and they have that spherical shape. Here we're going to be looking at L equals 1 orbitals to start with. So these are what we call p orbitals. And there is no such thing as a 1p orbital because L has to equal 1. If n equals 1, L cannot equal 1, which is what you would have to have for a 1p orbital. So the first set of p orbitals are the 2p orbitals. We call the 2p subshell, to use that terminology again. And the 2p subshell consists of 3 orbitals. So unlike the s orbitals, we only have one s orbital per shell for 1s, 2s, 3s. For p orbitals, we get the 3 orbitals that we show here: 2px, 2py, and 2pz. Now these are named after which axis they point along in the mathematical solutions. So we have, these are all the 90% of probabilities found within these shapes. We're not going to look at the probability, the psi squared function for these p orbitals, but you can look at a very similar sort of plot. It's just now we have stuff happening with the angles too. So it's a little bit more complicated to try and represent it. So we usually just use these representations where the 90% of the probability is inside these shells. So the 2px orbital points along the x-axis, the 2py orbital points along the y-axis, and the 2pz orbital points along the z-axis. Otherwise, they're the same, the same size. The electrons are on average the same distance from the nucleus in all 3 of these orbitals. And they all have the same characteristic shape that all p orbitals do, this sort of dumbbell shape, where we have electron probability on this side and on this side, and with another node here, right? This is a node just like we saw in the previous video, an area where the wave function goes to 0, the probability goes to 0. So p orbitals all have this shape. They all have these 2 sort of dumbbell sides to it. And the difference between the 3 different orbitals, these all have different values of m sub L. So hopefully by seeing this over and over, so we have one of these corresponds to -1, 1 to 0, 1 to +1. It doesn't really matter which one is which, it just matters that there are 3 different ones. So p orbitals have this sort of dumbbell shape. Now, one common misconception you may think about is when we're talking about probability, you may think, okay, so there's some chance the electron's on this side. If there's a 0 probability at this node, if psi squared equals 0 here, how does the electron get from this side to this side? But that's thinking about it the wrong way. That's thinking just in terms of particles. But this is all wave. This is all wave mechanics, the quantum mechanics. And so we don't have to think about the electron needing to get from one side to the other. It has a probability on both sides. So it's not like moving from one side to the other. It's just, as a wave, it exists on both sides simultaneously with some certain probability of being there. So rather than thinking about an electron traveling through this node, the electron's here and here. There's an and there, right? It's not that it's in either or the other place, it's in both places. Similar to how a standing wave, like again, coming back to this picture, if we think about a wave that's traveling up and down like this, and there's a node in between, the wave doesn't have to do anything special to get from one side to the other side of this node. It just travels along and just happens to have a node there. Remember, electrons are waves, and so trying to think about them as little tiny balls doesn't really work, which is why we need all the math behind this to get these shapes. Okay, so the whole point here being to say, these have a different kind of node. This is what we call an angular node, meaning there's a specific angle at which the wave function is 0, and that's just meaning in between the 2 lobes here. So each p orbital has one angular node, one node in between the other, the 2 different lobes that we have. So these are all L equals 1 orbitals. Again, we have 3 different ones, and you can have different values of n that you could have. So we will also have 3p orbitals and 4p orbitals, and etc. They'll all have the same shape, but similar to what we saw with s orbitals, these will be bigger, right? If we get to higher values of n, the orbitals get larger. Same story as we had with the s orbitals. Now let's look at the shape of our last one we're going to look at, which are the d orbitals. So these are L equals 2. So there is no such thing as a 2d orbital or 1d orbital. These are not allowed because the value of n and L don't match. So the first set of d orbitals, the first subshell of d orbitals, are the 3d orbitals, the 3d subshell. And because L equals 2, we have m sub L can be -2, -1, 0, +1, or +2, which means there are 5 orbitals. And those 5 orbitals are depicted here. So these ones have even more fun names. Rather than just px, py, pz, here we get 3dxy because it points in between the x and y axes, 3dxz because it points between the x and z axes, 3dyz, same reason, between the y and z axes, and then this 3dx squared minus y squared where it points along the y and x axes, and then the really fun one, the 3d squared, which looks a little bit different but is mathematically equivalent. The electron's the same distance and everything, but we have some lobes that point up and down, and another one that goes around the middle, kind of like a belt or donut around the middle part of it. So these are the set of 3D orbitals, again the 90% surfaces for probability. And you may notice the shape has changed even a little bit more from the p orbitals. So we started with nice ball for the s orbitals, p orbitals have 2 lobes, and d orbitals have 4 lobes. We'll call these lobes, meaning there are 4 spots right here, 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 and here, where there's probability for the electron. And again, we have now two sets of nodes. It's probably easiest to draw it on this one. So we have one node that's right here, and another node that's up and down here. Now, something you may be noticing is that the number of nodes, number of what we call angular nodes, is equal to L. Right, so now that we're at L equals 2, L equals 0, s orbitals had no angular nodes. We have these what we call radial nodes, meaning specific distances. But for L equals 2, we have 2 nodes now. So the number of angular nodes is equal to L, and the total number of nodes for any orbital that includes both angular and radial nodes is equal to n minus 1. So it's that same value that we had when we're looking at the s orbitals. But s orbitals have no angular nodes, whereas this combines both these angular nodes where it's a specific like plane or angle that where the wave function goes to 0 versus a specific distance where the wave function goes to 0. Okay, so, but we can, again, just like our previous orbitals, we can have 4D orbitals or 5D orbitals. We can have other subshells, and these will get bigger. So same trend, as n increases, these orbitals get larger and larger. Okay, and so that's the basics of shapes for p orbitals and d orbitals. In the next video, we'll look at how electrons fit into these atoms and how the energies of these orbitals matter and how we sort of fill up the electrons in an atom.